Hi, hello, welcome to section 6.4 of chapter 6. As I promised, things are going to get a little bit easier for you from this section on. Trust me, I don't lie to you. So, what we did so far is heavy lifting in this chapter, especially section 2, where we focused on electronegativity and dipole moment, um, polarity, partial charges. If you feel those topics are harder, I'm with you. They were, hard to grasp for many students. That's why I spent like 1 hour, 15 minutes on a topic, just make sure that I covered everyone. And in section 3, chapter 6, section 3, where we worked on drawing Lewis structures is also one of the challenging topics for students, not for everyone, but for majority one, I would say they struggle tiny bit, and but with the correct guidance, they will do fine. I hope that I get it right. My method that I used for past couple years has been working wonders for my students, and you are my students, and you shouldn't be any different in getting it right. All right. So what we are going to do in this section is that we are going to learn a topic called formal charges. Like in the first example, if you remember section 3, when you draw structure ClO3 minus, and I told you to not to bother about that negative charge for a moment because I'm going to discuss it here. And when you draw the structure Cn minus, again, I told you there that don't worry about the negative charge for now because I'm going to cover it here. So, and I also told you like, you shouldn't draw structure like that. You should draw like this, like, in the case of ClO3, I said like put Cl in the middle, put oxygens in the outside because it's going to lead you the right way. Because it all comes from practice and also seeing enough examples, and also working with the formal structure, formal charges. So here I'm going to show you how to calculate the formal charges. It is the charge on a non-covalent atom in a molecule, basically. So formal charge. So because of one atom is having more bonds than it should, or one atom is having more lone pairs than it should, they end up with some charges. Not because they were ions, it is because they kind of end up with wrong number of bonds or wrong number of lone pairs than they should. We shouldn't even say it wrong. More number of lone pairs or more number of bonds than they should, which results in either negative charge or positive charge. So we are going to learn how to calculate the formal charges so that when you draw Lewis structures, you would try to avoid them by cross-checking the formal charges like in step 8. Uh, in your step 8, you were supposed to calculate the formal charges. I didn't discuss it there because I didn't tell you how to do it here. So we are going to do it now. You are going to learn how to calculate formal charges, then apply it on Lewis structures, then then find the correct way of drawing a Lewis structure if you find your structure has more charges than it should. Because when you draw Lewis structure, your goal is to have a structure with the lowest possible number of charges, if not at least zero charge. Okay. Let's see what we got here. So as it says here, formal charges can be used to determine the most possible Lewis structure when more than one possibility of Lewis structure exists for a compound. What it means is, when I give you a chemical formula, technically you can come up with a structure that follows all first 6 rules, but it fails to have the lowest number of charge, the rule 8. So if you make a mistake in rule 8, end up with more charges than you should go back and correct your structure. That's what rule 9 says in the Lewis structure rules. So even though you can technically draw more than one possible structure, only one structure is more preferred than another. The one that is preferred is always either neutral or least number of charges. Okay, so to determine that, you need to know how to calculate charges first. So this is how you would calculate formal charges. Again, I titled it as a textbook method because I am going to introduce my own personal method, which is students' favorite. But I'm just going to show you for a second, because if you see it anywhere else, you would recognize what it is. You wouldn't feel foreign to this, or if you like it, you can use it. But almost all of my students use my method of calculating formal charges. So how do you calculate formal charges is you would use the total number of valence electrons of that particular atom and subtract the associated electrons from it. You would need to identify what are the associated electrons are. They were all non-bonding electrons like lone pairs and half of the bonding electrons. So that's how you would calculate it. Now let me show you my method. So my method is that you're going to use this informal style to identify the formal charge. Yeah, nice rhyming. So this informal style is that formal charge is equal to group number minus whole total of sticks plus stones. So I am explaining what are sticks and stones. Let me just cover what is a group number is. Group number is what you find it in the periodic table. Like carbon group number is 4, nitrogen group number is 5, oxygen group number is 6, fluorine group number is 7. They were group numbers. Just need that, very easy to identify, right? And you need to know what our total sticks and stones are. I like this because it is very easy to remember, sticks and stones. How can you forget about that? This is the easiest thing you need to remember in chemistry class, right? Sticks and stones. That's why I guess my students like that. So sticks are defined as the number of bonds, like lines, sticks, lines. So, to avoid any confusion, I elaborated a single bond is 1 stick, a double bond is counted as 2 sticks, a triple bond is counted as 3 sticks. So how many number of bonds it is connected to, you will say those many sticks you have for that atom. And the stones are number of electrons in the form of lone pairs. Let me repeat that again. Stones are number of electrons in the form of lone pairs. So what it means is one lone pair has 2 stones. If you have a 1 lone pair, we have to count it as 2 stones. Now we are going to practice what we just learned. Okay, take notes of this. In the next slide, I'm going to practice and show you how this works. All right. So the question is asking us to determine the formal charges on each oxygen atom in the ozone molecule. Okay, let's do this. So I'm going to use my method of group number minus sticks and stones. So for that, I'm just going to write formal charge. Group number for oxygen is 6. I'm working on this oxygen. Group number is 6, right? And sticks plus stones. There are currently 1 and 2 sticks for this oxygen because it has 2 bonds. And I currently see 4 stones. I guess I need red color pen here so you can see what I'm drawing. So there are currently 2 sticks and 1, 2, 3, 4 stones. So total is 6 minus 6, 0. The charge on that oxygen is 0. Let's count the formal charge on this oxygen. So formal charge is equal to 6 minus how many sticks? I see 2 on the left and 1 on the right. So 3 sticks. And how many stones? I see 1 and 2. So 6 minus 5 plus 1. So the charge on central oxygen is plus 1. Let's count the formal charge on this oxygen. So formal charge is equal to group number is 6 minus, there is 1 stick on the left side and 1, 2, 3, 4, 5, 6 stones. So 6 minus 7, which is equal to -1. So this oxygen has a -1 formal charge. That is how you would identify formal charge for each single atom. If you pay attention, the given ozone has no charge. How do you know? We didn't write any +1, +2, -1, -2, right? If you don't write anything, it is neutral. So what is the overall charge of this molecule is 0 plus 1 plus -1 is equal to 0. Yes, it has formal charges on individual oxygens, but the whole molecule is neutral. That's what we are looking for in the structure. So that is how you would identify formal charges and you would express it. Okay, let's work on a couple more problems. This is one of the easiest topics that you can get. So the problem here is saying that the widespread use of fertilizers has resulted in contamination of some of the groundwater with the nitrates. And nitrate is potentially harmful because nitrate, when it is entered the groundwater and when we drink that groundwater, that nitrate is converted to nitrate, NO2, which NO2 is mainly harmful to us because it hinders our ability to absorb oxygen because NO2 wants to bind with iron instead of oxygen. So it gets competed with it. So that's the trouble. We want oxygen supply to the body, right? So yeah, that's the story behind it. That's why, now and then you see in the news that, oh, we are testing nitrogen levels in this groundwater, in this Umatilla area, in some other area, which is, right thing to do. You just want to check those nitrate levels to keep people safe. But now you know why we need to check those nitrate levels. So the question is asking us, determine the formal charges on each atom in the nitrate ion, NO3 minus ion. So before that, okay, I have the answer here, but I want you to pause the video and draw the Lewis structure of NO3 minus on your own. Then we can work on, let's see, identifying the formal charges. I always ask my students to, draw the structure they come across. From now on, as a matter of fact, whenever you see a chemical formula anywhere in the textbook or anywhere, you should start drawing those structures. Practice drawing those structures by yourselves, because after a few tries or a few days or a few weeks, you will just get really good at it if you just have that mindset that you have to try drawing the structures. Okay, so I'm just showing you here. I'm going to quickly do it because we can save some time here. So on NO3, we have like 1 nitrogen, 5 valence electrons. Each oxygen has 3 valence electrons, so 18 and 5, 23. And negative charge is 1, so total of 24 valence electrons that I calculated. And I want to choose the central atom between nitrogen and oxygen. I'm going to go with the nitrogen because nitrogen is least alpha negative. And something tells me that oxygens are wanting to connect with the nitrogen. Okay. I used up 6 valence electrons to make these connections between nitrogen and oxygen. 24 minus 6 is 18. 24 minus 6 is 18. So 18 over 2 results in 9 lone pairs. LPR says lone pairs, shortcut I use. I'm going to use those lone pairs to give the octet number of electrons to all elements that are outside first. So oxygen has 2 currently, so it needs 3 lone pairs. Same with this oxygen and same with this oxygen. I did like 4 steps already, and I don't have any lone pair to give in step 5 because I used all 9 lone pairs. Then what do you have to do? In step 6, you ask the outside atoms to be kind to the central atom because whole molecule needs to be stable, make a double bond. So if you do that, this one only left with just 2 lone pairs, but these both oxygens left with 3 lone pairs. Now we are saying overall charge is -1. Okay. Now I want you to identify how is that. I'm going to erase this work, and we are going to use this space here to calculate the formal charges on each of these oxygen. So, because there are too many oxygens, I'm just going to label them 1, 2. Again, the oxygen on the left is same as oxygen on the right, so you just don't have to identify for both of them. So I'm just labeling them as one type of oxygen and second type of oxygen and nitrogen. So first formal charges for 1 oxygen. right? So formal charge is there, group number minus, I see only one bond for oxygen, that is titled 1, but I see 6 stones, so the charge is going to be +1. And oxygen titled 2, the formal charge is going to be 6 minus, I see 2 sticks and 4 stones, so the oxygen is 0. And the nitrogen formal charge is, group number is 5. I see total of 4 sticks and no stones, so charge is going to be +1. Actually, you would have already noticed it by this time. Sorry about that. That should be -1. This one should be -1. Okay. Now we are saying overall charge is -1. Let's see how do we got that. So you have -1 charge here, 0 charge here, -1 charge here, +1 charge here. Do you already see it, or you want me to highlight? Sorry. -1, -1 is -2, +1. Overall, it becomes 1, -1, because this is 0 anyway. This is how you would calculate the formal charges and make sure every atom has the correct formal charges. Okay. I'm just going to show you the work, but I already showed everything, so you don't have to pay attention to it. So I'm going to go through it quickly. We already worked on it in the previous slide. Let's see. Let's discuss the reasons why you need to worry about lowest charge Lewis structures, and if at all you end up with a structure that has Lewis formal charges, how to choose the correct one. So whenever there is a more than one possible Lewis structure, a possibility, these are the things you need to cross check, like step 8 in that rules list that I gave you. This is what it discusses basically. So a Lewis structure in which all formal charges are 0 is preferred. If at all possible, let's try to get a Lewis structure with no formal charges at all, because that indicates more stability. More neutral is more stable. We want molecule to be more stable rather than really reactive than what we need. So if at all possible, try to get a structure where all formal charges are 0, because it is preferred. Okay. If not possible, at least look for small formal charges. Don't try to get a molecule with too large formal charges, even though you're technically correct. It's not going to be a stable structure. When we ask you to draw a stable, when we ask you to draw a Lewis structure, we meant to ask you to write the most stable Lewis structure. If you either get a Lewis structure with lowest formal charges, or at least a small formal charges, that's kind of automatically fell into the category of most stable formal charges structure. And this is very important. Formal charges should be consistent with the electronegativities. This is very, very important. Remember, when I discuss the electronegativity, it is going to keep coming back. This topic is something that you need as long as you are associated with chemistry, or as long as you are associated with any biological sciences like biology, biochemistry, anatomy, physiology, because just using one single concept of electronegativity, you can explain lots of stuff, lots of reasoning that you can come up with. So formal charges should be consistent with the electronegativity. What it means is, let's say you have a chance to give a negative charge between two elements like nitrogen and oxygen. Nitrogen is less electronegative than oxygen, so oxygen, which is more electronegative, which says that it can hold more electrons, should have that negative charge. So don't try to give the nitrogen a negative charge and oxygen positive charge, which is against their character. They don't fit right in with that special environment. So what it means is, look at this structure here. This is best possible structure. When we say, get a structure that with Zero charges, this is best possible structure. Each atom in CO2 has zero formal charge. Fantastic. This structure is wrong because you have a possibility that you could get a structure with no formal charges at all. Then why would you want to draw a structure with a plus and a 0 and -1 to reach the overall charge 0? You shouldn't draw a structure like this when there is a possibility that you could draw a structure with everyone having no charges at all. Okay. Let's see. So formaldehyde, CH2O. I think I already had answered that I don't want to show here under strategy, but it's fine. Formaldehyde CH2O, which can be used to preserve biological specimen. Most of the biology guys already know about this, I guess, is commonly sold as 37% aqueous solution that called as formalin, if you're looking for a name. Use formal charges to determine which skeletal arrangement of atoms shown here is the best choice for Lewis structure of CH2O. This is what the question gave, and this is the basic framework they gave. So what we are going to do is we are going to use both of these frameworks and draw structures out of it. CH2O has what? How many electrons? Carbon has 4 hydrogens, 2 hydrogens, 2, and 1 oxygen, 6. So the total is 12. Okay. So in the basic structure, 1 bond, 2 bond, 3 bonds, and 1 bond, 2 bond, 3 bonds. So each structure used 6 electrons, so there are 3 lone pairs to use. And how did we come up to this structure is to this. We have 3 lone pairs. We gave it to the most electronegative atom first, compared to just changing pen color so you can clearly see. Okay, and now oxygen has octet electrons, but carbon doesn't. So you are going to convert one of the lone pair to a double bond. That's how you come to this structure. Okay, and how do you come up to this structure is you use 3 lone pairs to put it on oxygen, but carbon here in the center has no 8 electrons, only 6. You converted one of the lone pair to draw this structure from this structure. Okay, I'm going to erase this now because we got our answer. Now we are going to check which one of these structures are better possible structures, because it has to do with the formal charges. Now we are going to identify formal charges. We don't have to ever identify formal charges on hydrogen because they were already terminal element. They can only make 1 bond. If they make 1 bond, it is neutral. So you don't have to identify it. We are going to identify formal charges on these 2 atoms and on these 2 atoms. Okay. So carbon formal charge is group number is 4 and I is minus 3 sticks and 2 stones. So 4 minus 5, -1 charge. And oxygen, let's see if I did it right. 3 sticks and 2 stones, yes. Oxygen formal charge is, group number is 6 minus 3 sticks plus 2 stones, 6 minus 5 plus 1. Okay, so it says -1 and plus 1. Okay. Now let's come back to this carbon. So the formal charge here is group number is 4 minus 4 sticks and 0 stones. Formal charge is 0. And formal charge for this oxygen is group number is 6 minus 2 sticks plus 4 stones. Group now formal charge is 0. So The structure here has 0 formal charges on both the elements, and the structure here has +1 and -1 here. So this one is least preferred and this one is preferred. As the structure on the right has no formal charges at all, which is what you're looking for if you're hoping to draw a most stable structure. That is how you would use the formal charges. You should easily be able to identify formal charges. Again, it's not a complicated formula. You just need to put your work in. Just need to correctly identify how many bonds there are, how many single electrons there are. Then you can apply this formula, group number minus sticks and stones, identify charges. Then you would know what is the correct way of drawing a structure. Then you would understand after a few structures that this is the wrong way of drawing structure. You cannot draw structure like that, but this is the right way of drawing structures, keeping the carbon in the middle and add more atoms to the carbon. Again, it comes with the practice. Don't get worried if you make a couple mistakes. That's all part of learning, especially with Lewis structures. Try to embrace making mistakes, because it's going to happen. You are going to make mistakes. That's why I need you to practice a lot, so that you would only make those mistakes when you practice, not in the test. Not in the test. Right? Good luck. I'll see you again in another part of this chapter.